So my probability to get an even number is how many wanted outcomes? One, two, three, four, five blue squares, so that's 5 out of 10. What's the probability of getting a number greater than 5? That looks like 4 out of 10. The probability of getting an even or a number greater than 5 is 5 out of 10 plus 4 out of 10. Take away the probability that you got both an even number and a number greater than 5. 2 out of 10. 4, 7 out of 10. Okay, so it's kind of easy to see how why this rule makes sense. You don't want to count that 6 and that 8 twice. It's both a blue and a purple. You only want to count them once. So we subtract that 2 out of 10 to keep from counting those numbers twice. Okay. Complementary events. The probability that an event or its complement occurs is 1. Okay. So, a couple of complementary events. With your deck of cards, you could have red cards or black cards. They're actually red suits and black suits, aren't they? And that's all you could get. You could either get a red or black. Probability of red is 1/2. Probability of black is 1/2. So the probability of red or black is 1/2 plus 1/2 is 1. Oh, C. It's not always abbreviated with a superscript C. I can't remember what there's another abbreviation that they use in our textbook that I can't remember what it is. But anyway, in stats we use the little c. Okay. So here we go. Probability of getting a 5-card flush in poker. All 5 cards the same suit. 1, 2, 3, 4. There we go. 5. Is about 0.002. There's a 5-card flush. Numbers don't have to be in order. Okay. What's the probability of not getting a flush? So, getting a flush or not getting a flush? 0.002. Oh. Plus whatever this is has to equal 1. So the probability of not getting a flush, 1 minus 0.002 or 0.998. Okay, and I want to do one more example, or maybe I just want to start the first homework problem. We'll do that. Let's run through the first homework problem. See what I like better. Because the first homework problem asks you to apply your knowledge, apply this little bit of knowledge to a problem with a pole. So I want you to see how to do that. Okay? Pollsters are always concerned. You got your little books? Does anybody need a little book? Pollsters are always concerned with the response rate among people they survey. A recent poll contacted 84 people in the 18 to 21-year-old age group, and 11 refused to respond. So I start taking a few little notes here. In the 18 to 21-year-old age group, 11 refused, and there were 84 people. So how many actually responded? "84 people were surveyed, 11 refused to respond," which means the rest responded. So that's 73. Okay. They also contacted 275 people in the 22 to 29-year-old age group, and 20 refused. And that was 275 total, which makes 255 actually responded. Okay. That's 359 total people. Okay, that's what the problem says. That's good. What is the problem? We're going to pick. Okay, assume one person is chosen from these 359 people. I don't know what age group they're in. I don't know whether they refused to respond or responded. Let me just pull one of these 359 names out of the hat. What is the probability that this person is in the 18 to 21-year-old age group, or didn't respond? Okay. So the probability of being in the 18 to 21-year-old age group is 84. Yeah. I'm sorry, what? Oh, thank you. No. Oh, it says refuse to respond. Oh, you're on problem 2. I'm on problem 1. Okay. All right. So the probability of being in the 18 to 21-year-old age group would be, there's 84 of those out of our 359. The number of people who refuse to respond, 20 plus 11 is 31 out of 359. Now I got to count the number of people who are in both groups. They're in the 18 to 21-year-old group and they refuse to respond. I have 11 of those that are 18 to 21 and refuse to respond. You're sure that's never mind? Yeah. Okay. And that becomes 84 out of 359 plus 31 out of 359 minus 11 out of 359. Point 4? Huh? 104 out of 359. Okay. You can leave it as a fraction or turn it into a decimal.